What was Einstein's biggest mistake? Though humans have long wondered how the cosmos came to be, for the vast majority of human history, we lacked the appropriate mathematical and physical tools to reliably describe it. Only when Einstein developed his theory of general relativity did things begin to alter in the 20th century. This idea proposed that time and space were both relative and that the fabric of space-time was bent by gravity. The speed of light in a vacuum was also constant across all reference frames. Further research demonstrated that general relativity may also foresee the creation of black holes and the bending of light caused by enormous objects. This evolved into the most accurate hypothesis we have for explaining the world in which we live. After presenting his hypothesis, Einstein started to test the cosmos, but while doing so, he made what he later described as his greatest mistake in history. But what error was this? And was it really an error? Get the answers to these and other questions by watching this video with me. Albert Einstein's theory of general relativity included a term known as the cosmological constant in 1917 to force the equations to predict a stationary cosmos in line with scientists' theories at the time. The cosmos was later shown to be expanding, not static, and Einstein abandoned the constant, calling it his worst folly in life. The Greek capital letter lambda stands for Einstein's cosmological constant, which has recently been reintroduced by scientists to explain the enigmatic dark energy that appears to be counteracting gravity and speeding up the expansion of the cosmos. In summary, the cosmological constant, or lambda term, that Einstein first proposed does not appear to be a mistake in the strict sense of the word because it really assisted astronomers in explaining a key aspect of the cosmos. This may be where the film ends, but why did Einstein and other scientists favor the notion of a stationary universe? And what about dark energy do we know? We must take a step back and consider the state of the world before Einstein in order to respond to the first query. Before Einstein, Newton's theory and his proposed cosmological model were the finest theories we had for explaining the nature of the cosmos. According to Newton's theory of gravitation, gravity is caused by mass, and the resulting force is always attracting. Many and well-known examples of Newton's theory's empirical triumphs can be found. Prior to this century, all gravitational phenomena observations were, with a few minor exceptions, consistent with Newtonian theory. Newton's cosmological model ruled out the possibility of a finite cosmos. In reality, observations made at the time indicated that you would not be able to see any movement of objects in the sky above the moon, sun, and planets. Newton concluded that the universe was static as a result of this. In other words, it didn't seem to move very much. Based on this presumption, which his observations appear to have confirmed, Newton concluded that the universe must be infinite in size. The matter at the edge of a finite universe would be attracted by all of the other mass in the universe and eventually be dragged towards the center of the universe if everything in the universe is attracted to everything else, according to Newton's law of gravitation. If it occurs, one would observe matter near the universe's edge traveling in that direction. However, during observations, this wasn't noticed. The universe wasn't contracting inwards, which was the obvious result. Having more mass farther out, which prevented the other material from being drawn inwards, was the only method to keep the most exterior mass from falling in. What about the bulk further out? You may then inquire, will it not be drawn in? Not if there is even more junk, that is. If you continue thinking along these lines, you will eventually arrive to Newton's cosmological model of an infinite universe. Hence, Newton's theory of an infinite universe naturally provided an explanation for the observed static universe. He didn't understand all of the motions that we can observe now since his equipment couldn't pick them up. As of right now, we are aware that the universe is not static. This cosmic model, meanwhile, has some flaws. If the cosmos were endless, for instance, it would follow that there must also be an infinite quantity of mass. If this were the case, you could go outside at night and see the sky filled with objects. But when we step outside, we don't always see something in the sky. In fact, there are many spots where nothing is visible. This is referred to as the Olbers paradox, and another way to think about it is to wonder why the night sky is dark if the cosmos is endless. We would observe a considerably brighter sky with a constant brightness, day or night, if the cosmos were limitless. Hence, this was Newton's theory of the universe. Yet, as soon as Einstein presented his theory of general relativity, he attempted to develop a new cosmological model to see whether it would address some issues the Newtonian theory left unresolved. Although it's difficult to visualize because it should be a four-dimensional object, Einstein believed that the cosmos had a finite amount of substance and was closed, like a sphere. Throughout this video, assume that Einstein's universe is spherical. You could travel through the universe starting from any location on this sphere and finally return to your starting location. In essence, despite the fact that the space was finite in size, one might have traveled the entire universe and not have seen an edge. We were being given a new perspective on the universe by Einstein. The cosmos becomes spherical when matter adds a curvature to it, eliminating the need for the universe's mass, and consequently, bright objects, to be infinite. The Olbers conundrum was nicely resolved in this manner. What about the still universe, though? Astronomers at the turn of the 20th century continued to believe that the universe was timeless and unchanging. How might Einstein's theory account for this? Well, a consistent solution required the addition of a new term to the relativistic field equations in order to justify this. Several others felt that the new quantity, known as the cosmological constant, damaged the symmetry and clarity of the original field equations and was essentially a fudge factor. But it is a little-known fact that Einstein had mentioned the possibility of such an extension to the field equations in his original explanation of 1916. General relativity unquestionably permitted the word. It didn't take long, though, for Einstein to be disproven. Young Russian physicist Alexander Friedmann proposed in 1922 that models of the universe should take into account non-static solutions to the Einstein field equations. Friedmann constructed two differential equations from the modified field equations that relate the density of matter and the cosmological constant to the time development of the cosmos. Friedmann's contribution was not well received by Einstein. His initial thought was that the Russian had made a maths mistake. Georges Lemaitre, a Belgian physicist, later used the modified field equations to obtain time-varying equations for the universe's radius in 1927. At the time, studies of the spiral nebulae's recession velocities suggested that the universe was expanding rather than remaining static. These nebulae were later recognized to be entirely distinct galaxies from our own, lying outside the Milky Way's boundaries. Lemaitre connected the new astronomical findings to general relativity by arguing that the data showed an expanding, not static, universe. This idea did not make Einstein pleased, however. As Lemaitre recalled, Einstein had labeled his theory of an expanding cosmos abominable. Yet 1929 marked a sea change in society. Astronomer Edwin Hubble published the first conclusive proof of a linear relationship between the nebulae's recession and their radial distance during that year. Many physicists took Hubble's findings as proof of the universe's largest-scale expansion, and numerous relativistic time-varying models of the cosmos were suggested. After ultimately giving up, Einstein published two independent models of the expanding cosmos in the early 1930s, one with closed spatial curvature and the other with a flat shape. He opted to drop the cosmological constant in both situations, claiming that it was producing redundant and unstable solutions. Einstein's biggest error was this. In his essay, he argued that the inclusion of a constant cosmological element in the equation of gravity must be rejected and that the cosmological constant would not have been included if Hubble's law had been understood at the time. Yet scientists later discovered that the biggest error wasn't actually an error. Scientists Perlmutter, Schmidt, and Rees determined that the universe's expansion is speeding up in 1998. The acceleration is being caused by something, and this substance is typically referred to as dark energy. It is presently believed that this dark energy makes up 73% of the universe's matter, far outweighing the 23% of dark matter and the 4% of conventional matter. Astrophysicists discovered that the cosmological constant must be introduced once more in order to explain the universe's accelerating expansion. This constant, like in Einstein's static world, would imply a negative pressure acting on the cosmos, which would cause it to expand more quickly. For their discovery, Perlmutter, Schmidt, and Rees were given the Nobel Prize in 2011. We may jokingly remark that Einstein was correct even when he believed he was incorrect. This narrative actually teaches us that no one is flawless and that there are many challenges on the path to science. In this situation, it is our responsibility to persist and never give up, since we can always learn from our failures. Here's where the video ends. Thank you everybody for watching. What do you consider to be Einstein's biggest mistake? Please share your thoughts in the comments section below.